Alright, so now that we know what a scatter plot is about, which is, it shows the relationship between two quantitative variables, let's dive into scatter plots a little bit deeper, but also discuss it in the context of the shape of distributions. And what I want to do is I want to create a scatter plot where I have on the x-axis the GDP per capita, so that would be this column, and on the y-axis the fertility rate. And let me first create a new sheet, and I call that scatter plot. And so I'll just copy quickly the data and put it here. Maybe center it. Okay, so now in this case the fertility rate is shown first. And what I want to do is I want to highlight the data just like this, and then I press on Insert, Recommended Charts, Scatter Plot. But as I mentioned earlier, I want to have on the x-axis GDP per capita, and by default Excel will always put the first column on the x-axis. So what I want to do quickly, I just want to switch those two. Okay, so now this is our data. So now let's take a look at what the scatter plot looks like. So we highlight the data, then we go to Insert, Recommended Charts, and there's already the scatter plot. And here's our scatter plot. Let's put it up a little bit. So now the question is, actually before we go into it, maybe we want to label it a little bit. So we said on the x-axis we had GDP per capita, GDP per capita, and on the y-axis we had a fertility rate. Okay. So if you look at this data, we can already see the higher is GDP per capita, and that's the independent variable. The lower is the fertility rate. Fertility rate is the dependent variable. So the fertility rate obviously depends on GDP per capita, at least if we draw it like this. And now let's add the trend line, just as we did in the previous video. And now the question is this a good or a bad line of best fit? And the answer is, it is obviously a bad line, because it would suggest that if countries that have a GDP per capita of more than 50,000, one would predict or estimate that those countries should have a negative fertility rate. And then of course that doesn't make any sense. And it also seems that in the range between, let's say, 10,000 and 30,000, the trend line is always above the actual values. So the line of best fit doesn't really describe the actual data pretty well. And the problem why that is has to do with what we call non-linearity. The data is not linear. This scatter plot is probably best described by a nonlinear function, like some kind of a curved line, and we can play around with this. So there are like other trend line options, so maybe more options. So for example, we can check exponential. Let's remove the linear. Okay, now it's a little bit better, but still bad, because it still will predict negative values. Let's play around with other trend line options. Maybe, what else do we have? Logarithmic, what will that do? It's basically as bad. And we can use a polynomial maybe. trend line, more options, maybe polynomial, order 2, it's also not great. So the point that I'm trying to make is that you need to make sure that your data is good. And what we have here is actually very bad data. So a line of best fit would probably look something like this if I try to draw it by hand. You know, maybe this would be a good line of best fit. But then it becomes also difficult to interpret. So, but the question is, why is this data not conducive to a nice scatter plot? And the answer is because the data is not normally distributed. So let's review again quickly, and let's take a histogram of GDP per capita, go to recommended chart, all chart histogram. Okay, so we can see that GDP per capita has a very long right tail. So this here is the histogram GDP per capita. So this is not normal. What about fertility? What about the fertility rate? Let's highlight it and insert recommended chart. And let's go to histogram. Okay, maybe not as extreme as the histogram, but even here we would suggest there's a little bit of skewness to the right. So what we like to do in data science and statistics is we want to get rid of that skewness. And the good thing is that we can often do so when data is skewed to the right, which fortunately is quite often the case with data that we use in business and economics and other social sciences. We can linearize the data. So what does it mean when we say we want to linearize the data? So let me just make that a little bit smaller. And let me illustrate the idea of linearization. So let's assume we have data which looks essentially like this. So maybe this is our variable x, and the first value is a 1. And the next one is maybe 10. And then we have 100. And then we have 1,000. And then we have, let's say, 10,000. Okay, so now this data is nonlinear because the distance is constantly increasing. And that's a little bit the same as here. We have an increasing distance to the right. And so the data is not linear. So how can we make it linear? And the answer is we can take the log. So as you know, if we take the log, before we take the log, what we know is that, for example, 10 raised to the 0, 10 raised to the 0 is 1. 10 raised to the 1 is 10. And 10 squared is 100. And 10 cubed is 1,000. And 10 raised to the 4 is 10,000. So now if we just take the log of x, what we see is we get now here, so the log of 1, that's a 0, and then the log of 10 base 10, that's a 1, and that's a 2, that's a 3, that's a 4. So now what you see is that we linearized our data, which goes up from 1 to very high values, just like our GDP per capita. Most of the people have low and middle incomes, but there are some countries that are very, very rich. And here, this nonlinearity, by taking the log, we get something like 1, 10, 100, 1,000, 10,000. We can convert it into something with linear, a linear pattern like 0, 1, 2, 3, 4. So, okay, so maybe I'll make that a little bit smaller too. And let me add again the trend line. So this is bad. So now what I do is I create another column and I call it log of y and log fertility. Okay, so I'll just say equals the log, and that is, here's the log 10, for example, and we can take the natural log 2. But to stay with this example, I take the log base 10, and we do the same for the fertility rate. And now I copy this down, and I remove the formula, Control A, copy, right click, paste special values. Okay, so now let's first take a look at the scatter plot for the log of y. So insert, recommended chart, all chart, histogram. And let's pull it up a little bit. So let's put it here next to it. So you see it already looks a little bit more normal. So if I were supposed to draw like a distribution line, this has this long right tail, but here it already looks a little bit more normal, not perfect. Okay, and here this was the histogram of fertility. Histogram fertility. Now let's take a look at the log of fertility. Okay, insert, recommended chart, all chart, histogram. Okay, so maybe it's difficult to say if this improved it dramatically. There are statistics for it that we could use, but yeah, we don't have to talk about that right now. And so that would be the histogram of log fertility, and here this is the histogram of log, just call it now y. Even the histogram of the log of fertility, I mean, this clearly seems to have this long right tail, and here, maybe a little bit better. But what the linearization of the data does becomes definitely clear once we take a look at a scatter plot. So now I generate a scatter plot where the log of GDP per capita is on the x-axis and the log of fertility is on the y-axis, and we have to compare it to this original scatter plot. So insert, recommended chart, all charts. Yeah, there was already their scatter plot. I'll take this one. Okay. So now what Excel does is it displays everything from 0 to 3, but so that value is like 3. So what I do is I don't need to have on the x-axis everything from 0 to, let's say, 2.5. So what I quickly want to do is I format the axis, and I'll just say the minimum on the x-axis is actually 2.5. Okay. So now let's put a trend line here. And now you can see that this trend line is obviously a much better fit than here, because this trend line describes the data now on average much better than here. Here we had like weird things, you know, that we would predict negative fertility rates, but that problem is clearly ameliorated by taking the log. So this is just an application for you to see why the distribution of data is important, and why it is important to know what your data looks like. Just one final word. Of course, whenever we display the data in terms of logs, like here, so here we would have the log of y, and on the y-axis we have now the log of fertility. In this case, we have to interpret our results differently. We'll talk about that maybe more when we talk about regression, but just some heads up. The regression coefficient that we can display, so we can actually go here and add the equation. So there's the option display equation on chart, and we can also do that here. More options, and trend line. So display equation on chart. Okay, so here we have a value of negative 0.39 if you round it. Technically this 0.39, which is the slope, and the 1.9, that would be the intercept, but this negative 0.39, that is what we call an elasticity. And that will tell us that a 1% increase in GDP per capita will reduce, on average, the fertility rate by 0.39%. Here, the slope is something like a very small number, like 0.0000 something, and that would be interpreted as a $1 increase in GDP per capita reduces the fertility rate by 0.000 or whatever that is. But anyhow, so the point that I was trying to convey in this video was that the distribution of data is important whenever you work with data, and what you typically want to have is data that is nicely normally distributed. If the data is not normally distributed, and very often it is skewed to the right, then log transformation can make your data more linear and then also more usable in order to work with them in a meaningful way. Okay, so let's stop here, and yeah, that was just like the overview over graphical visualizations of qualitative and quantitative data. Okay, just let's stop here.